In this example, we're going to simplify the expression and determine where the expressions are not equivalent. And we're also going to compare the two graphs on Desmos. So, with that being said, we're going to, in order to simplify a fraction, you need to look at the factors. So we're going to have to factor the top and bottom expressions in terms of polynomial factoring. So starting with the top, if I want to factor it, because it's not in standard form, I'm going to rewrite it in standard form as negative x squared plus 4. Then I would check for a common monomial, and since the leading coefficient is negative, I'm going to pull out negative 1, making it negative 1 times, in parentheses, x squared minus 4. And now I'll finish trying to factor it by, since there's two terms, checking to see if it's a pattern. It does indeed follow the a squared minus b squared pattern. So overall, my factors will be the negative 1 from the monomial, x plus 2, and x minus 2. So negative 1, x plus 2, and x minus 2. On the bottom, there is no common monomial, so I'll start off by, since there's three terms, multiplying first and last, giving me negative 10x squared. The combination that multiplies to be the middle term will be positive 5 and negative 2. And since there is no leading coefficient, we can jump from here straight to the factors of x plus 5 and x minus 2. When you are simplifying a fraction, you just want to cancel out the common factors between the numerator and the denominator. So looking at the factors on top and bottom, the common factor is x minus 2. So I'm going to cancel them out, leaving me with negative 1 times x plus 2 on top and x plus 5 on the bottom. You can also write this as negative 1x minus 2 over x plus 5, where you distribute the negative 1 back through. However, most teachers would accept either version as the simplified product. So I usually leave it as this. Okay, now for the other parts, we need to take a look at where the expressions are not equivalent. And we're going to take a look at Desmos before we actually do that part. So I've graphed here the first one in Desmos, and now I'm going to graph the simplified version in Desmos as well, which is a fraction with negative 1 times, in parentheses, we have x plus 2, and then over x plus 5. So as I type the rest of it in, you can see that they actually overlap. In fact, they overlap everywhere except in one particular spot. If you recall, the factor that canceled out was x minus 2, which has a root of positive 2. So at positive 2, if I can get it to pull up, let's see where I was there. There you go. It pops up just for a second there. It's really hard to keep my finger in the right spot. But you can see it comes up as 2 undefined, and you see an open dot forms as I get to the correct spot. Now if I go to the simplified version and go to x equals 2, you'll see that there is no open dot. You can see that it actually has a value there. So it's not undefined there with the simplified version. And that's because the factor that was creating the hole is now gone. That factor of x minus 2 doesn't exist in the simplified version, which means the simplified version exists at that point. So these two expressions, the original and the simplified version, exist or are the same everywhere except for x equals positive 2. So they're equivalent except when x is positive 2, but also wherever the other factor, the x plus 5, equals 0 as well. So at negative 5, it's not equivalent as well. Since at negative 5 there was the vertical asymptote, which they can't be equivalent if they don't actually exist in that spot. So everywhere but 2 and negative 5 is where these two expressions are equivalent. In other words, the original factors of the bottom determine where the functions exist and therefore where they could be equivalent at. And also this brings us back to holes and asymptotes and stuff. So if we were to write equations for those spots, x equals -5 is where we have a vertical asymptote, because the factor still remains after simplifying the expression, while x minus 2, since the factor cancels out, creates a hole at x equals +2, where x minus 2 would be equal to 0. Okay, in this example, we're asked what is the product of these two rational expressions multiplied together. We're going to be assuming non-zero denominators. This just means that we won't have to state the restrictions on the domain of the expression, or where the original and the simplified version are not equivalent. So as I go and do this, whenever you simplify fractions in terms of multiplication, we typically look at the factors on top and on the bottom. Because of how multiplication works, where you multiply straight across the top and straight across the bottom, and then cancel out common factors, we are able to just cancel out the common factors right away. So what we would do is we would try to factor both expressions in terms of polynomial factoring. However, these are monomials, so they're already as factored as can be in terms of polynomial factoring. So we would just look for common factors on the top of the fractions with the bottom of either fraction. So if we start with the top left, the factor of 2, does anything in the bottom share a common factor with 2? Well, the 4 does. So we would divide each of them by 2, canceling this out, forming 1, and making that a 2. Now I don't always rewrite it, but I'm going to rewrite it for the purpose of this. But we'll end up with 2yz on the bottom and just xy on the top left. Now just moving from left to right, looking at the x next, checking for factors of x in the bottom. There are no factors of x in the first fraction, and there's no factors of x in the second fraction, so they don't cancel out. Looking for factors of y, there is a factor of y in the left fraction, so they are going to cancel out. And then for the 3, there are no factors of 3, and there's no factors of x's in the bottom as well. So we're just going to go ahead and write it as a single fraction now. So on top, what we have is x times 3x squared, which will give me 3x to the third. And on the bottom, we have z times 2z, which will give me 2, that's a horrible 2, 2z squared. And just as a reminder, if the exponents aren't completely the same like they were for these y's, you would just subtract the exponents. So if it's like x to the third on top and x to the seventh on bottom, you would subtract the exponents, and since the bigger number's on the bottom, we would have x to the fourth on bottom. Or if we have x to the seventh on top and x to the third on the bottom, when we go to simplify that, subtract the exponents, with the bigger one being on top, we'll put the result on top as well. So just as a reminder, since the exponents happen to match on this particular example. Okay, in this example, we're going to be simplifying the expression and assuming non-zero denominators, so we don't have to worry about stating the restrictions. So just going through, I like to kind of start by factoring this first one and working in that direction. For some reason, I don't know why I usually go in that order, but it doesn't matter the order you factor in. So starting with this top left one, there is a common monomial. I think that's actually all we can do. Sometimes we might have to rewrite it a couple stages of factoring, but I think there's only a common monomial of x to the third, and it gives me x plus 7. Again, sometimes we might have to factor it farther, but we can't factor x plus 7 any farther because there's no exponents. The next one, the 7x squared plus 35x, if we go and try to factor that, well, The common monomial between the two will be 7x, which will actually give me x plus 5 left over. And again, since there's no exponent with that, we're not going to be able to do any more factoring with that. Next, we have the x minus 8. X minus 8 has no common monomial, and since there are no exponents, I can't factor it in terms of polynomials, so we just bring it down. And lastly, x squared minus 3x minus 40. There's no common monomial. However, since there's 3 terms, we can multiply first and last and try to factor it that way. So the factors of negative 40 that adds up to be negative 3, I believe, are going to be negative 8 and positive 5, which means our factors are x minus 8. Since there is no leading coefficient, we can jump straight to the factors, and x plus 5. Okay, now we're going to just go through and look for anything that we can cancel, any common factors on top and also on the bottom. So starting with x to the third, is there any x's connected to only things by multiplication in the bottom of either fraction? Well, here we have a regular x. So the regular x in the bottom is going to cancel out entirely, and this one is going to reduce to x squared. There are no other x's in the bottom that we can reduce this x squared with, so we'll move on to the next factor. Before we do though, sometimes people will mistake that we can cancel out this x squared with this x. We cannot, because this x is connected to something by addition, subtraction, therefore it is not a factor by itself. Next, since we can't reduce x squared any farther, we'll move on to the x plus 7. There are no x plus 7s in the bottom of either fraction, therefore we cannot cancel out x plus 7 with anything. X minus 8, there is not an x minus 8 in the first fraction, however in the second fraction there is, and because there's an x minus 8 in the bottom of the fraction, we can actually cancel those out. Next we have x plus 5. X plus 5 also occurs in the bottom of the first fraction, so we are able to cancel them out so long as one is in the top, one is in the bottom, and the two fractions are connected by multiplication. So we have canceled out everything we possibly can. Let's figure out what we have left, writing it as a single fraction. I see my x squared still, and I also have x plus 7. On top, that's all I have on either fraction, and we'll write it as just a single fraction here. And on the bottom of the two fractions, all I have is a 7. No, we cannot cancel out these two 7s because the one of them is connected by addition, subtraction to something else, so it is not a factor. You can only cancel out common factors when you're simplifying fractions. So this is overall the final simplified answer. You can also rewrite it as x to the third plus 7x squared, distributing the x squared through, though typically you often see it written like that. So. Okay, division is very similar to multiplication. The only difference is before you can actually simplify it, you have to deal with the division sign. The way you divide fractions is you keep the first fraction the same, change it to multiplication, and then flip the other fraction, the second fraction. So keep, change, flip is one of the things people often say for that. The actual thing that's going on is to divide fractions, you multiply by the reciprocal. Now we just have to go through and do the same thing we did before. We factor everything and then cancel. So it looks like b minus 5 and b plus 3 is already factored for us. So we're going to just bring it down. The 8b plus 20, it looks like it has a common monomial of 4, so we can pull out 4 from both terms, which will give me 2b plus 5. Next one is 6. 6 is a monomial itself, so we can't factor it in terms of polynomial factoring, so we're just going to bring it down. And then lastly, 4b plus 10, there's a common monomial of 2 that goes into both, and we'll get 2b plus 5. So I factored each of the expressions. Now we just have to see if we can cancel. I usually just work from left to right on the top fraction, seeing what is common in the bottom. So b minus 5 is my first factor. There are no b minus 5s on the bottom of either fraction. B plus 3, no b plus 3s. 2 is a regular number, so looking at the bottom of either fraction, we actually have two numbers that can reduce with 2. It doesn't matter which one you choose, but you can only reduce one of them with 2. I'm just going to choose the 6. So I'm going to divide this by 2, giving me 1, and divide this by 2, giving me 3. Let's see, we also have, it looks like 2b plus 5 on top and 2b plus 5 on the bottom. Two fractions are connected by multiplication, so we can cancel them out. Now we just have to finish this off and write it as one fraction. So across the top, we have 1 as the monomial, but we don't need to keep the 1 unless it's a placeholder. And then we have our b minus 5 and b plus 3. On the bottom, we have a 4 in the one fraction, a 3 in the other fraction. So 4 times 3 gives us 12. There's no other factors in the bottom, so it's just 12 in the bottom. So this would be our simplified expression. You could also distribute out the top, but usually this is fine leaving it like this. Okay, in this example, we're going to be simplifying another expression. This is a complex fraction where we have a fraction on top of a fraction. And again, we're going to be assuming non-zero denominators. You can see that right here, this one, this division sign is a little bit thicker, a little bit longer. It stands farther than the other fraction bars. That means this is in the middle. That is an important detail when you're choosing how to go about doing it. So that means this in the bottom is a single expression, a single fraction, and this on top is a single fraction. The middle bar here signifies that we're taking the expression on top and dividing it by the expression on the bottom. The process would change slightly if that fraction was in a different spot. For instance, if it was 4x squared minus 1 with the long fraction there, and then x squared minus 4 over 2x minus 1. So it changes, how you approach it changes depending on where that long fraction bar is or where the parentheses are. So in a situation like this where this fraction bar is longest, that would mean this would be in parentheses and this would be in its own parentheses as well. So how you go about doing the keep, change, flip would be different depending on where that middle fraction bar is. Okay, with that being said, fraction bars really is just division. So I'm just going to do keep, change, flip like we did for the division one. We'll keep the top fraction, that's our first fraction, the same, 4x squared minus 1 over x squared minus 4. We'll change it to multiplication and we'll flip that bottom fraction, x plus 2 over 2x minus 1. Now it's just a matter of factoring everything and then canceling. So starting with the top left again, it looks like there's no common monomial. However, both terms are perfect squares, so it follows the a squared minus b squared pattern, whose factors are a plus b and a minus b. Which means the factors of 4x squared minus 1 are 2x plus 1 and 2x minus 1. The second expression in the bottom left here, there is no common monomial, and again it happens to be both perfect squares. The factors of that one are x plus 2 and x minus 2. Our next expression in the bottom right, 2x minus 1, has no common monomials, and since there's no exponents, we can't factor it farther. And the last expression, x plus 2 in the top right, again, no common monomials, and since there are no exponents, you can't do anything else as far as factoring. So everything is factored, so let's look for common factors on top and bottom to cancel out. 2x plus 1, there are no 2x plus 1s in the bottom of either fraction. 2x minus 1. 2x minus 1 doesn't occur in the bottom of this fraction, however, it is in the bottom of the second fraction, which means we can cancel those two factors out so long as the two fractions are connected by multiplication and one's on top, one's on the bottom. And then lastly, we have the x plus 2 on top. There's also an x plus 2 on the bottom. Again, we can cancel out those two x plus 2's. Rewriting what we have left as a single fraction, we only have 2x plus 1 on top and x minus 2 on the bottom.